In this video, we're going to discuss different methods of cross-development for the Apple II on the Apple II Pi computer system. So here I've loaded up the Apple II user using it right into the Raspberry Pi OS GUI, and I want to show a few different methods that we can use for our cross-development purposes. First thing I want to do is I'm going to load up our terminal program, and we're going to go right into the A2 term program so we can see that we are in AppleSoft. Drill down to AppleSoft from our terminal window. And that's so we can really kind of interact directly with our Apple II hardware, because we're going to open up another terminal window and we're going to use this and different Linux tools to build some software that we can run on our Apple II directly. So the first thing I want to do is I made a little directory of some source files here. I have 3 different versions of a hello program. I have one in assembly, one in BASIC, and one in C. Now, my favorite lightweight GUI editor is Geany. So let's use Geany, and we're going to open up the very first one. Let's use our hello basic file. And here we can say a very, very simple little AppleSoft program. Now, in an earlier video, we showed how we can use the A2 term program to run basically an exec file, to copy a file as if we had just typed it in. And that's how we're going to get our AppleSoft program into our AppleSoft session. So over here, from our Linux terminal session, we are going to basically copy this file, this hello.basic BAS file, right into our AppleSoft session. Come back over here, we can see where it showed up. We can list it now, and now we can run it. And there we see how to get AppleSoft source code right into our Apple II AppleSoft session for running and testing. But we have the benefit of being able to edit our source code right in a nice Linux GUI editor, Geany. There are very many to choose from, but this is actually my favorite lightweight GUI program. Let's continue on. We have an assembly file. Let's open that real quick. I call this one hello.a. Now, this is a very, very simple little program, and it's written using the Acme 6502 cross assembler. This is a tool used in a couple different projects, and the Lawless Legends team uses it for the compiler for all the assembly code, and Plasma uses it as a back-end assembler for assembling the code generated by the compiler. So this one, a little bit longer than the basic version, but not too much, and it's probably somewhat self-explanatory. It just loads our X register with 0, loads the accumulator from this message label down here. The Acme does use a little bit different style pseudo ops than you may recognize from other assemblers, but it's pretty straightforward. We check for 0, and you can see at the end of our string I put a 0 value in here so we can terminate it, and it will exit when it gets to 0. Otherwise it will actually set the high bit, which the Apple II wants, calls the character out routine, and keeps looping until it finally gets to the null terminated string. So let's come over here. Let's see how we can build that here. And it's pretty simple. We use Acme. We're going to tell it where we want it to start running from. So in this case, I'm just going to use hex 2000. Let's set the output file. We'll do a hello.bin, and we're going to assemble hello.a. Now we have our hello.bin file, and let's come over here just to see what's going to happen. We can load our hello.bin into the address that we set as the start PC. Gets loaded very quickly. It's a small little program. Now over here in our AppleSoft session, we are going to enter the machine language monitor. We loaded that thing at 2000 hex. Let's see what we find there. There we go. That looks like the code we just assembled. Let's run it and see what we get. Hey, there it is. What do you know? We see it's hello Apple II Pi from assembly. We're going to return back to AppleSoft. And we still have our AppleSoft program there as well, because we loaded our machine code at a higher address. And that's one thing you will start to have to take into account as you develop directly on the Apple II hardware, is there are additional programs and code running. You're running in the AppleSoft environment. You have to be aware of HiMem, because the Apple II Pi client lowers that somewhat so it can insert itself into the upper memory. And so you really have to be careful stomping on other things. But for the most part, you have all the memory from 800 hex on up to about 9,000 hex-ish available for your use. Now, one thing I'll put a link to is I'm running this all on a single monitor. If you're doing things that involve graphics or very specific Apple II output functions, is you may want to run with an external monitor connected to your Apple II in addition to your Apple II Pi, Raspberry Pi GUI monitor. In fact, I used this exact same environment when I developed the Apple II GS's NTSC artifact colors, the next generation talk I gave at Kansas Fest many years ago. I'll put a link to that video in the description here. Why that was interesting is I could cross-develop all my algorithms and easily put that and run that on the Apple II GS right there on the same computer, so I didn't have to worry about moving files back and forth. I couldn't use an emulator because emulators didn't emulate the type of functionality I was playing with. So it really required physical Apple II GS hardware in order to develop these algorithms. So look at that video. In fact, the presentation, I used that same system I developed it on. One monitor was connected to the Apple II Pi, the Raspberry Pi output for the actual presentation of the slideshow. The other monitor, or projector in that case, was connected directly to the output of the Apple II GS, showing off the NTSC artifact colors that I had been developing. Anyway, so that's just kind of the a real-world use case of this kind of a cross-development environment and how it was very, very useful. So the next little environment I want to play with a little bit is the CC65 C compiler. The 6502 is not really the best CPU when it comes as a target for a C compiler, but the CC65 toolset is quite impressive. It includes not only a quite reasonable C compiler, but also a very sophisticated assembler and a very sophisticated linker. So a lot of the things, including the ROM code for the Apple II Pi card, was all developed using the assembler and linker from the CC65 toolset. So here we're just going to do a very quick little C program. We've all seen this if you're a C programmer. It's the standard, print hello. So about as simple a C program you can get. However, let's see how we can build this on our Linux window. It requires a couple steps. I'm not using a makefile. I'm just typing everything in by hand. So we are going to run CC65. We have to tell it what type of computer we're building this for, because it can support Commodores, Ataris, a bunch of different ones. So we're going to set the type for the Apple II. We're going to compile our hello.c, and that generates a hello.s. So this is the assembly language file. Just to show you real quick. There it is. That's our assembly language file. Now we need to disassemble this with CA65 hello.s. And that gives us a .o file, which we now have to link with LD65, again telling it we're an Apple II. We're going to link our hello.o, and also we need an apple2.lib file. This creates good old a.out file for us. Something to be aware of, the CC65 environment for Apple II will create a file that requires an external loader to load the resultant binary into the Apple II and run it. However, that's if you're just running plain Jane ProDOS. Since we are running the Apple II Pi and can put this file anywhere we want, we can skip that actual loader itself, but we have to take a few things into account. So, real quickly, let's look at the configuration file. Oh, gotta go to the right file. It's under user share CC65. There we go. Now, how this linker file defines our resultant binary, we'll scroll up here. It sets our start address at hex 803. So in the Apple II memory map, that's kind of like where the basic code starts as well. So 803 is our start address. However, we do have a header that is prepended, and our header here is 3A hex bytes long. So that actually begins 3A hex bytes before our start address. I'm pretty good at hex, but I can't quite do that in my head. Luckily, Linux to the rescue. We're going to load our little calculator here. We're going to put it into scientifics mode in hex mode. so that we can take 803, which is our start address, minus 3A, which is the header size. This is actually going to provide us with the load address. That's kind of like at the end of the text page on the Apple II. But this is exactly where the loader program from the CC65 toolset will load the resultant binary. So all we have to do is go back here, make sure we see all our files. Our A.out is what we want to load. We're going to load that. In fact, actually, let's do something even more fun just to show that it gets loaded properly. We'll go back to the monitor. 803 is where our program will get loaded. You can see right now it's actually, that's where our AppleSoft basic program was loaded. So it's kind of a code for basic, not actual 6502 code. However, we'll go back to our terminal window here. We are going to bload A.out, and the address is OX, because it's in hex, 7C9. All right, 7C9. We have loaded our generated binary file. Let's see what we have at 803 now. Aha! Now we have something that looks like 6502 machine code. Let's see what we get. We're going to run it. Bam. Hello, Apple II Pi from C. Notice it's all uppercase because the C runtime assumes it's like an Apple II, so that was uppercase only, so it makes everything all uppercase for us. I'm sure you can go into the CC65 documentation and figure out how to enable lowercase output. But there we go. We have just compiled, loaded, and run a C code program on our Apple II Pi very, very easily. Very simple. Now, that was 3 versions of code that we could develop and run directly on the Apple II Pi. Some environments are a little more sophisticated, including Plasma. So, let's get that. We're going to clone the Plasma project right into our directory here. We have Plasma. Let's go in here. We can look at the files. We want to go into the source directory. Now we're going to make test. So this is a make file. First it will build the entire Plasma infrastructure, starting off with the Plasma VM, the Plasma compiler, and then it will compile all of the system libraries, the examples, the samples, and in this case, the test program that will use a portable Plasma virtual machine here for Linux and spit out the output from this test Plasma program. Our Raspberry Pi isn't the fastest computer in the world, but here we go. It has now it just finished building the entire Plasma environment and run our test program right here. And so this little test program just runs through a bunch of little samples of code to ensure that it compiled properly, it ran properly, and got the right results. So it's a little sanity test thing that I wrote a while ago. However, to run this on the Apple II is a little more difficult because Plasma is an entire environment that runs on the Apple II. So we can't really run it under the Apple II Pi environment like we did the previous examples. However, we can use a bunch of other tools that we have available to us under Apple II Pi. One of the things that probably was overlooked along the way is that our Apple II GS emulator has taken advantage of some of our Pi drives. Our Apple II GS emulator actually maps our util volume. So if we look under our mapped drives, we have utils over here. It just so happened I have configured the Apple II GS emulator to map that drive under itself, so it shows up as a drive under the Apple II GS emulator. So what we can do, if we list our files here, here's the two test program or test modules that we just built and ran here. I want to copy these into our utils directory, which is our shared, if you will, disk image. So here I am going to copy these to and so this is copying the files through the Apple II back to the PyDaemon into those to the util disk image. Let's list that and see what we get. One thing I want you to pay attention to is the file names that we use when copying to the ProDOS imaged directories. Is it uses the same sort of metadata that CiderPress established, and what it does, it uses this little pound symbol here, and the first two characters represent the type byte of the ProDOS file, and the last four characters represent the aux type of the file. Linux doesn't have a way to put some of that metadata into alongside the file name, so I sort of inserted that into the file name just like CiderPress did, so the files are compatible between that tool and the files used to copy with Apple II Pi back and forth. So one thing I also did with this utils directory that you may not have noticed, it actually has a full Plasma implementation loaded in that directory structure. Another thing you may not have noticed, we can run the Apple II GS emulator in a window here in our desktop GUI. So we're going to bring up our GS emulator. As it comes up, you'll see it mount all the disks it sees. Here's utils, the util disk. This is the same one that we just copied our test program to. In fact, here they are. So I want to run Plasma inside the emulator. This is the Plasma command line system. And to run this test program, I do it like this. It runs it and outputs, and it better output the exact same thing that our portable VM output over here. So you can kind of see that, yeah, pretty much matches, at least at the end here. We can't scroll back the window on the emulator. The emulator doesn't real-time keep the files consistent with the disk image. So whenever you copy files back and forth, you will actually have to exit the emulator, but it's quick to boot and restart every time you want to try something out. So we can leave our emulator after we've tested it out there. Nice thing about the emulator also, there is a debugger that's available with it that's a little hard to use, but it has saved the day a number of times for me, being able to go in and debug some machine state that was just basically impossible to do under the physical Apple II hardware. All right, so here we are. We want to test this out on the real Apple II. Now, we can't do it really from the A2 term, but what we can do, we're going to get out of this for a moment, but we're going to switch our input to the Apple II. Now, earlier we showed you how to exit the Apple II Pi client, which is what we're going to do now, because we want to use our Apple II just as an Apple II. We're going to exit back to ProDOS. I remember, so here's the utils Pi drive that we've been using all along, now being used directly from our Apple II. I'm going to go run Plasma. Here it is. This should look just like the version of Plasma we were running in the emulator. Once again, here is my test module. Run that. Runs a bit slower because it's the actual Apple IIe Platinum at 1 megahertz as opposed to a supercharged emulator, but we get the same program running that we saw earlier. Now, if we want to get back to our Apple II Pi client really easily, all we have to do is just do a full-on reboot. So I'll use the Open Apple Control Reset. It will reboot off of the Apple II Pi card and route us back to Linux. That easy. We can go back to Linux. We still have our interactivity, and that's how we can cross-develop on our Apple II Pi, either directly on Apple II hardware or Apple II emulators, all using sort of the features available to the Apple II Pi environment. So I hope that was an interesting little exercise for you. Thanks for watching.